Okay, so at the beginning of class on Wednesday, I didn't mean to imply that homework is due at class, but obviously some of you are handing it in at class, and that's fine. Just like with the with putting them in the slots, with completion on the left, graded on the right, I assume that's what happened here. Go in alphabetical order. I want to once again remind you about the fact that we got this Mathematica assignment due next Tuesday, and once again, it takes quite a while to read through. There's a lot of stuff to read through. I think it's all good stuff, so you should do that. I will say that when you open up these sections, you should certainly go ahead and enter the code that you see here and experiment with it. Go ahead and change it, by the way. You're not getting graded on my code that you're entering and seeing what it does. You can make changes to that. What you're getting graded on are those exercises, okay? And again, I think it was there's 5, I believe, exercises 2, and then I think 5, 6, 7, 8, and 9 or something. And you find them in these different sections. You have to open them up. This first section here has exercise 1, which I think is what you skipped. The next section here, kind of a long section. It's got exercise 2 in there, and some other ones that I think you skipped. But go ahead and read the rest of it anyway. It's good stuff. I think you skipped these, etc. Okay, you find these exercises by opening these things up. You can work in groups, just like on your graded assignments. I think you're going to get more out of it if you're there working together, watching any videos that might be helpful, discussing stuff, that kind of thing. I mean, maybe you can read it ahead of time before you meet. That's probably a good idea if you read it ahead of time. And yeah, things that say optional are optional. They're just for your own interest. Certainly on a first read through, I wouldn't bother clicking on any of the links. You probably don't really have time. But I ideally mean this to be something that's useful for you in the future. So I'm hoping that at least some of you might go back in the future and look back and explore things further. Okay, so again, that's due on an off day next Tuesday by 2 p.m. Any questions about that? All right, let's spend a little bit more time with population modeling. Then we're going to go ahead and think about a mixing problem like we had for the graded assignment. And if you decide after I go through the mixing problem, it's going to be a different one. But after I go through the mixing problem, then you, for some reason, want to make a change, you can. Although of course you have the key anyway, so hopefully it wasn't a problem. What I'd like to do here, just briefly, with the population model, is we saw this particular exponential model didn't work very well, except for the first 60, 70 years or so. I do want to emphasize that you could sort of unscientifically try to modify the exponential model in various kinds of ways to see if you get a good fit, if you can modify it to get a good fit. And you can easily do that with Mathematica's manipulate command that will allow you to change the 3.9 there and the 0.03065 right there until you get a decent fit, perhaps. Or maybe you won't ever get a decent fit, but you can certainly give it a try. So I could call this P0 for the initial population instead of 3.9, although that if I'm going to change that, it won't necessarily match the initial population of the entire country at time 0. I can also change the coefficient of the t. I'll call it k, like the book does. And let those two quantities, the p0 and the k, be animation parameters that I allow myself to change. If I use syntax 0 and 0, looking like this, that's syntax that in the manipulate animation is going to cause P0 to start at the value 3.9, but allow me to change it to go as low as 1 and as high as 6. And I can do something similar for the K. Let's see, no, I guess I'll start at 0.03. Go as low as perhaps 0.01 and as high as, say, 0.06. So initially, it's going to look pretty similar to the previous graph because those starting values for P0 and K are similar. However, now I can change these things and see if I can ever get a good fit. So here I'm changing the k. That's a better fit perhaps when you're around 100, 110, 120 than before, but still not so good over here, and it does maybe worse near 60 or 70. So you might try adjusting P0. You can keep adjusting things, but what you're seeing here as I continue to adjust these parameters is you never get a very good fit overall. So what that's telling me is the exponential model probably is not the way to go. The exponential model, again, worked pretty well the first 50, 60, 70 years with those initial values of P0 and K that we found from the first 2 data points. But you're never really getting a good fit over all 210 years. Okay, so you might want to try a logistic model, for example. I'm not going to take the time to test a logistic model in class today. What I would like to do with the logistic model is check by hand that this function that you see here really works, though I think I will pick specific values for P0 and K to make the calculation simpler. Again, our textbook doesn't tend to use that phi notation that I've been using. When you do your homework problems, for the most part, unless I tell you otherwise, you can do what the textbook does and not bother putting the phi in there, okay? However, in class, I will often write the phi in there, and I'll do it again now. A couple reasons for that. One reason is other textbooks use it, and so if you ever needed to use another textbook, you'd be more comfortable with that perhaps. Secondly, I do want to emphasize that even though we're okay with the sloppy notation sometimes, it really is sloppy, and to be less sloppy, I should give the function a name other than y. Technically speaking, though, we don't worry about that as far as, I won't mark you wrong if you don't do this, okay? Third, it's going to set us up later in the class, especially in chapter 3, for doing some pretty neat things, okay? So we want to get used to this. I'm also going to do some things in this with chapter 1 that are perhaps going to continue to be confusing, but we keep working at it, keep trying to get better at it. Let me go ahead and pick some values again for P0, N, and K. Again on the board and in the book, N, the carrying capacity is capitalized in Mathematica. You don't want to do that because a capital N is reserved for numerical approximation function. I won't usually bother putting subscripts on Mathematica, but when I write it by hand, I'll put a subscript. And I usually make my K's cursive. Let's pick nice numbers. Let's pick, say, P0 is 10, N is 100, and K, let's let the 2 above that. That would represent, at least initially, it would be like 200% growth, which is way too fast. We're just after nice numbers to check that this function works. So plug in those numbers here. N times P0, 10 times 100 is going to be 1,000. Got to go across this thing here. E to the 2t is on top. I'm going to look back over here again at this formula. N minus P0 is going to be 100 minus 10 is 90. And then we also have P0 times e to the kt. So I've got a 90 plus 10 e to the 2t. I claim this function solves the differential equation. Show this solves the differential equation, DiffEQ, also called an ODE, for ordinary differential equation. dy dt equals k is 2, got a p there, and then a 1 minus p over 100. Right? The equation had a k times p times 1 minus p over n. So I plugged in k equals 2 and n equals 100. I guess I have an initial value problem as well, P0 being 10. also satisfies the initial condition. Oops, I used a y there, didn't I? P of 0 equals 10. Okay, the initial condition is easy to check. Just plug in t equals 0. The checking there. I should have called this a P2, sorry. You can write P of 0, like the textbook does, that's fine. You can also write, if you use my phi notation, phi of 0. Again, that's the better notation, that's sloppy, but we don't worry about it. Plug in t equals 0. E to the 0 is 1, so you get 1,000 over 90 plus 10. 1,000 over 100 is 10. So verify that it satisfies the initial condition. That's the easy part. The hard part is going to be showing it satisfies the differential equation. What does it mean to satisfy the differential equation? Okay, again, this is the key thing that's most confusing at the beginning of this course. What does it mean to satisfy the differential equation? It means when you plug it into the left-hand side of the differential equation, which in this case is the derivative of the function, it won't always be just the plain first derivative of the function. Sometimes it can involve second derivatives and things like that. But here it involves just the first derivative of the function, dp dt, substitute this function into there. In other words, find its derivative. Calculate what the left-hand side becomes. And you can use any of these notations. Either of these notations. Or p prime as well. See what you get, and then also plug it into the right-hand side in place of the p. P is the function. Replace p with this function of t. Simplify, see if you get the same thing. If you do, then it's a solution. If you don't, then it's not a solution. What is the derivative here of this function? Well, we got to use the quotient rule. This looks like it's going to be kind of messy. Low d high. Right? Quotient rule. Looking at that fraction over there. Low d high minus high d low. Again, d high, low d high means derivative of the top. Minus high d low, the derivative of the bottom. Look at the bottom over there. Chain rule again brings you another factor of 2. So you get that. Over the square, what's below? Over the square of the bottom. 90 plus 10 e to the 2t squared. Kind of messy. Does it simplify nicely? Yeah, it does. At least nicer than this. You get some cancellation when you use the distributive property right there. You get 20,000 e to the 4t. But look over here, you're also subtracting the 20,000 e to the 4t. Those cancel. So the numerator simplifies to just 2,000 e to the 2t times 90. What would that be, 180,000? E to the 2t over the bottom. So that's what the derivative simplifies to. How about the right-hand side? Is it okay if I erase this? What does the right-hand side simplify to when you substitute the function? When you replace p with that expression. With the phi notation, when you replace p with phi of t. I'm going to go ahead and write it that way. 2 phi of t. I'm substituting phi of t in place of p. And then I do that substitution, I simplify, I see if I get the same thing in the end. of t is that. I substituted right there. Now I need to substitute right there. Oh, I think it's going to be worthwhile to subtract the fractions. Think of one other fraction. Think of it. You could think of it as 100 over 100. But when I put the phi of t in for there, I'm also going to have 100, this thing over 100. I can write that as one fraction, which would be ultimately mean canceling the 100 with 1,000 there to get a 10 on top. Let's see, is that worth doing? Ultimately, what I'm trying to get here is the fact that I want to ultimately think of this 1 as having, I think I want back the denominator. So I want to write the 1 as 90 plus 10 e to the 2t over 90 plus 10 e to the 2t. Yeah, now subtract this, which again means divide this by 100, which means cancel 1,000 to leave a 10. And lo and behold, when you combine those fractions by combining the numerators and leaving the denominator the same, the 10 e to the 2t's cancel, leaving you with just a 90. And then you can multiply the fractions. 90 times 1,000 is 90,000, times 2 is 180,000. You get the exact same thing. We have a match. Equality for all t. At least we're not dividing by 0, which we would not be for this example. For this example, this denominator is never 0. Actually, if I change my initial condition here, I could get a solution whose denominator could be 0. Like if I made my initial condition p0 bigger than n, that would happen. You'd have a vertical asymptote for the graph, in the graph. Does that make sense? Can I clarify anything that I did there? So it can be a bit of a pain. It's easy to make mistakes. I was a little worried about making a mistake myself. But that's what you do. This is not an accident. Okay, we use separation of variables to derive the solution. Here we're checking. Actually, the checking is also the showing. When you separate variables to find the general solution and the particular solution to an initial value problem, you're actually only logically showing the possibility of a solution, not the actuality. The checking really shows that the function solves the differential equation. So it's more than just checking that the answer is right, that you didn't make a mistake. That, logically speaking, is the proof, is in the checking. If you pick some other function, by the way, just randomly, and wondered if it's a solution, what do you think would be the answer if you somehow could pick a random function? Or if you did pick some sort of pseudo-random function. I don't know, is that random enough? What do you think is going to happen? It's not going to be a solution in all likelihood, okay? It's definitely not. We know what the general solution looks like from the other day. You plug it into the left-hand side of the differential equation, it simplifies to 2t. You plug it into the right-hand side of this differential equation, it does not simplify to 2t. What does it simplify to? 2t squared times 1 minus t squared over 100, and then I can multiply the 2t squared through it. It simplifies to a 4th degree polynomial. It doesn't simplify to 2t. T squared is not a solution of the differential equation. The left and right hand sides do not equal each other for all t in the domain. Okay? They could equal each other for certain values of t, but not for all t. this is not a solution. Okay, so we need clarity, first of all, in this class about what it means to be a solution. Now, that type of question probably will be on the first exam. Check that this thing is a solution or not even. For an example where I would give you a possibility, a differential equation maybe you couldn't solve in your own head, but I give you a function, you could certainly be able to check whether it's a solution or not. All right, let's go on to a mixing application. I'll make up an example different from your homework. In fact, I will make it harder than your homework was. So what I usually do is I imagine a vat. Okay, it doesn't have to be a vat, it could be a bucket or something. But I usually draw it like that. There's a vat. And I usually, for the sake of reminding myself that it's important to assume your saltwater solution, say, is well mixed, I usually imagine like some fans in here that mix up the salt, okay? The salt water, I should say. That looks like a fan. That looks like a clover. Yeah. Whatever. You got some fans in here spinning, mixing up the salt water. Why? So that you can keep the concentration of salt uniform, relatively speaking, or at least make that a reasonable assumption. Okay? You don't want the salt settling toward the bottom, you want it well mixed. So I usually I don't always draw it, but I usually imagine there being something inside there to mix things up. I will go ahead and erase these things now. Let's say, let's go metric this time. This is a 10-liter vat. Okay, not real big. 10-liter vat. And initially, let's pretend it's got 2 liters of salt water, although initially I'm going to pretend it's pure water. Initially, and this is pure water, no salt. All right, I'm going to pretend I've got salt water coming into the vat at a certain flow rate and a certain concentration. So you got water coming in at a certain flow rate in maybe liters per minute. Maybe 5 liters per minute. But you also are letting the mixture, the salt water, go out at a certain flow rate. And if I make this flow rate different, it's going to make the problem harder to solve symbolically. It actually will result in a differential equation that's not separable. You can't use separation inversions. Let's pretend this flow rate is 3 liters per minute. I didn't say the concentration of salt up here. Oh, maybe 2 grams per liter. Doesn't matter what you call the quantity of salt in the vat. In my answer key I called it S, but you could have called it A for amount or Q for quantity. I think I'll call it Q today. It's the quantity of salt in the vat. Use units that you're given in grams. T is going to be time, and it would make most sense based on the flow rates to be in minutes. Time since I started this process, since there were 2 liters of pure water here initially, and I turned on the flow and also drained the vat at the same time. The basic principle, the basic idea, is that the rate of change, the derivative of Q with respect to time, should equal the rate in minus the rate out, where these rates are of salt, not fluid. The units here should be in grams per minute, since Q is in grams and T is in minutes. dQ dt is going to be in grams per minute. These both need to be in grams per minute as well. Which means when you know the flow rate and the concentration of salt, you multiply those two numbers to get the rate of change of salt in grams per minute. The liters is going to cancel. So you've got 5 liters per minute. That's the flow rate of the salt water. The concentration of salt is 2 grams per liter. The liters are going to cancel, giving you 10 grams per minute. That's how fast the salt is entering, if you just think about the salt. How about its rate out? It's in the rate out that the well-mixed assumption comes into play. You're assuming at any moment in time that the salt water, the concentration, is constant over the entire mixture. It's going out at a flow rate of 3 liters per minute. So we again take the flow rate and multiply times the concentration. Excuse me. The concentration is the trickiest part. What do you think I should do for the concentration here? Any ideas? It is still going to be in grams per liter. If that helps. Got an idea?
Total salt divided by total liters in there.
Yep. Amount of salt, Q, divided by the volume in liters. I could initially write that as Q over V, V for volume. However, V is a function of T, so is Q, but because Q is the dependent variable for the differential equation, I don't want to put an of T next to the Q, just like you didn't for your simpler problem. You shouldn't have. Your equation for that graded problem here today was autonomous. In my key, I just had an S on the right side, no T's. You don't want to put a T there. You don't want to put a Q of T there, even though you need to on Mathematica. You do, however, want to put a T down here. This is V of T. In a way, when you've got an autonomous equation and you're plugging into Mathematica, so you do have T's on the right side, the only way they show up is next to the function name, Q of T, with the T in square brackets on Mathematica. If the T shows up in some other way, multiplying T times something, or dividing by some function of T, that's the way that the non-autonomous nature of this equation comes into play. So this equation is going to be non-autonomous. It's also not going to be separable. You won't be able to separate the Q and the T. And so we won't be able to use separation of variables. So we're going to need some other technique. But what is V of T? We want to be more specific about that. What do you think? Can I come up with a formula for V of T? Do I have to solve a differential equation to find V of T?
It's just 5 minus 3, isn't it?
It's related to 5 minus 3.
Plus 2.
2 plus 5 minus
minus
3
3
times
times
T. The initial volume is 2. The volume is going up at a linear rate. Its initial volume is 2. It's going up at a constant rate because these flow rates are constant. The slope is going to be 5 minus 3. The difference of the flow rates is going to be 2 as well. That's a coincidence that these matched. And so V of T is going to have the equation 2 plus 2T. So the differential equation now can be written as dq dt equals 2 minus 3q over 2 plus 2t. The water is pure initially, so q of 0 is 0. There is your IVP. It's not autonomous because of the t right there. Did I get it right?
It's 10 instead of 2.
10, yeah.
Oh, thank you. You guys are alert, that's great. 5 times 2 is 10. All right, yeah, 10 minus 3t over 2 plus 2t. All right, yeah, so this is non-autonomous, it's not separable. So what do? We use Mathematica, at least right now. In section 1.8, we'll talk about a technique for doing that by hand. Can Mathematica do this? Could we use DSolve, for example? Yes, we can. Q prime of t. I'm putting this in a list because I'm going to also have the initial condition in there. Q prime of t equals double equal signs. When you use DSolve or solve or find root, etc., you need double equal signs. What's the equation on the right-hand side? It's 10 minus 3q over 2 plus 2t, but in Mathematica, you got to put a t next to the q. That doesn't negate the autonomous nature of the differential equation. Or if this part weren't here, I meant to say. But the fact that this part is here means the equation is non-autonomous. Comma q of 0 equals 0. Then put a comma q of t, and then put a comma and a t, and square bracket. Mathematica says the solution is this. That's fairly, I think that's probably about as simple as it could get, perhaps. And you could try various things like expand. I guess that might be simpler. Or simplify. Let's see if simplify works. Here I'm using the / postfix operator. That's kind of nice. Except I'd like the 4 through there. These operations, when I use the // occur after the DSolve gets done. I also can do those in the ordinary way with square brackets. So I can go simplify, expand with square brackets. Like that, I get the same. Oh, I thought I could get the same thing. I guess I need to switch around the simplify and the expand. This is working from inside out. I forgot what order I did them in. The other one at the end was working from left to right. Anyway, there's a formula for it. So it's solvable. You just don't have the tools to know how to solve it yet. But it is possible. DSolveValue again is the other command that's new, and actually is going to be the one I mostly use. The benefit of DSolveValue here initially seems to be just that it makes the output simpler looking. Just the expression that defines the function rather than this other stuff. This other stuff that involves a q of t and an arrow is called a rule. Why it's inside this doubly nested list, I'm not sure. If you want to make use of DSolve, you got to use some tricks. Like if I want to store the output of DSolve in something I'll call SOL for solution. If I want to graph a solution, I don't want to graph it like this. Instead, what I need to do is a little trick. Q of t / dot DSolve. That would actually allow me to plot that solution now. I think I don't need to put a t there either. By the way, what's the domain of the solution? I should, before I make this plot, I should stop there and ask that. What domain is this valid for t's? What values of t? 0 to whenever it fills up. How fast is it going to fill up? T equals 4. So then it fills up, and then it would start overflowing if I kept going, and the model wouldn't be valid anymore. So this model is only valid where t goes between 0 and 4, so I should only graph it over that range. There it is. That's a plot of the salt as a function of time in grams. So that's a little strange. If you want to make use of DSolve, you got to do this slash dot thing, which stands for something called replace all. Don't worry about what it means. It's just what you have to do to make it work. DSolveValue is a little quicker. Let's see. I think if I just do set this equal to solve, I think I can plot that right away. Using the same syntax, which is again a little strange because you don't see sol of t here, you just see sol. Sol is this expression that is a function of, it defines a function of t, so evidently that's why we don't need it there. I think today I won't do this, but later on I'm going to show you that sometimes it's beneficial to get rid of the t there and store this as something called a pure function. This is confusing. That's actually sometimes beneficial, but I think for the moment it'll keep things simpler if I just put a t there. Okay, so there's the solution. We could find its values at various points. Actually, this is an example of where this is kind of deficient. I think perhaps I need to do something like, if I enter it this way, I think perhaps to find the value of the solution at time 4, I need to do another slash dot thing. I think I've got to do this, which is kind of a pain. Oops. Okay. It's kind of a pain to realize you have to do that kind of thing, to remember that. Okay. So there's actually a better way, but I think for today I'll leave it there. I don't want to do more than your brains can handle here at the moment. Okay? We'll come back to this and I'll remind you what all this stuff means in later examples and later days as well. What we should focus on though for the last 12 minutes of class, and we end at 9:55, something called the slope field. The slope field is a way to sort of predict what solutions are going to look like without actually having to solve the equation. Well, that sounds kind of nice. I'm going to define a function I'm going to call it f. And here I do need to call it an f, not a phi. F is going to be a function of two variables. T, and usually in our generic problems, y. But in this problem with the salt, I'm going to call the second variable q. I want f to be a function defined by the expression on the right-hand side of the differential equation. And if f only depended on q, that would be indicating the equation is autonomous. Here it's not autonomous, we need a t in there as well. Okay, I've entered that function. That is a function of two variables, q and t. And as a function of two variables, I can think of the q and the t as being both independent variables. Even though with the differential equation, I'm assuming t is the independent variable and q is the dependent. As far as the f is concerned, the f doesn't know about the differential equation. when I just think of it as a function. When I think of it in terms of the differential equation, then for the differential equation, t becomes independent and q becomes dependent. By the way, once I've made this definition, I can also use DSolveValue or DSolve in this kind of way. I get the same answer. Once I've defined the right-hand side function, I think I will usually call it that, the right-hand side function, I can use it within DSolve or DSolveValue on the right-hand side. Keep the t as a t, replace, in this case, q with q of t. If this were a y, you'd replace the y with y of t. You get the same answer, it's the same differential equation. The benefit of this right-hand side function, though, is that it allows us to plot the slope field. To plot a slope field in Mathematica, the basic command is called VectorPlot, which in general plots something called vector fields. And in fact, once we get to chapter 2, we'll be using it to plot vector fields. But here in chapter 1, we're going to be using it to plot what's called a slope field. And that's the syntax you want right here for the quote-unquote vector field you plot with VectorPlot when you want to make a slope field. You make a list. Curly braces indicates the list. The first entry of the list is a 1, always for slope fields, for scalar differential equations. And the second entry is the right-hand side function for the differential equation, whether it's autonomous or not. You pick a range for t. Even though negative t's are not valid for a model, I think I will go ahead and plot this for slightly negative values of t. And even though values of t bigger than 4 are not valid for our model, I think I will go ahead and plot it for values of t bigger than 4 anyway. I'll go up to 10. Let q go, say, from -1 to some positive quantity as well. I'll lay at least up to 20 based on the value we saw. Let's let it go up to 30, say. Q can't be negative for the model, though. Just to see the wider slope field, though, I'll include slightly negative values of Q as well. This is going to plot something that's not quite ideal as it stands. Yeah, that's not very nice looking. I can make it better by including an option called vector scale arrow. What I'm about to write seemingly has no rhyme or reason other than it works. Inside the list I'm going to put, I usually pick 0.03 comma 0.03 comma none. Why does it work? I'm not sure. I saw somebody else do it. I copied what they did. Okay? This makes it nicer. That's better. We can add more of these little line segments in here with this option called vector points. The default in both horizontal and vertical directions, I believe, is 10 or maybe 15. Let's see if 15 gives us the same thing. Yeah, that looks the same. It looks like 15 in both directions. So if I make it bigger than 15, like 30 for example, I'll get more of those little slope marks. Okay, that's too many. 5. Yeah. You gotta play with this to get it just to look nice. I guess I'll stop there. Okay? What does the slope field represent? Well, let me add some axes. By default, it puts it in a frame. Let me get rid of the frame. Frame arrow false. Let me put in some axes. Axes arrow true. Probably should label the axes. Quickest way to do that is like this. On the Mac, I can highlight highlight the T and the Q and make them bigger. And I tried using control on the PC and it seems to have stalled. Oh. Let's not worry about making this bigger. There's some things you can do with commands called text and style to make them bigger, and also italics, so it looks nicer. Oh, and it crashed or something and got rid of the F. If that happens, what just happened? Mathematica crashed evidently or something, and it got rid of the F in its memory for some reason. Mathematica 10 seems to be worse that way. Where's the solution in this, and what is this telling us? Well, let's go ahead and graph the solution in here. Show combines graphic objects. I think I'll end my vector plot after the vector points, and also put a regular plot in here of my solution function, which I'll just enter as this expression. Copy and paste it over here. T equal to P04, plot style, thick arrow, thick red, I'm going to say. There's my solution in the slope field. Hey, that looks kind of nice. That solution seems to be following the slope field. As if those little slope marks are telling it what direction to go in, right? What are we really doing when we're drawing the slope field? We're drawing, for this example, the values of this expression, like f of t comma q, in a tq plane. At any point, say you take the point t equals 2, q equals 1. I'm plotting a little line segment, say centered on that point, whose slope is the output of this function at that point. What is f of 2, 1? Plug in t equals 2, q equals 1 into this formula. Get 10 minus 3 over 6. 10 minus 3 sixths, 10 minus 1 half. 9.5. I want to draw a little slope mark with the slope of 9.5. Now, the scales on these axes don't match, and so a little slope mark right about there, which is close to the 0.21, I guess it would be down a little bit, doesn't look like the slope is quite steep enough to be 9.5. If you make, you can make the axes have the same scale if you do aspect ratio, arrow automatic. Now they're the same scale, and the slope there looks higher, closer to what it should be, 9.5. And how's that related to the solution curve? Well, essentially the differential equation is saying this. Give me a minute here. The solution, or a solution, is going to be a function whose derivative, whose slope at any moment in time, t, and at any output value, q, equals the output of this function at that point. So a solution curve going through this point, 2, 1, at a certain moment in time, well, when t is 2 and q is 1, the slope of that solution has to be, dq dt has to be given by the output of this right-hand side function. That's what the differential equation is saying, so to speak, about solutions and their slopes. That's why the solution has to follow the slope field. Those little line segments are like mini tangent lines to the solution curves anytime a solution curve passes through the midpoint of one of them. A real important idea. All right. Have a good weekend. See you on Monday.